Hello and welcome to our webinar devoted to the topic Tips for Designing Custom Coiled Springs. I'm your host, Lacey Cantrell, Marketing Manager for MW Components. For those of you who are not familiar, MW Components manufactures stock and custom parts for several industries and applications. I'm joined today by our presenters, Chris Koska and John Kahn, who represent two of our spring manufacturing facilities. Chris Koska is the Plant and Engineering Manager at MW Components Schiller Park, previously referred to as Mohawk Spring. He has over 18 years of experience working with customers in spring applications, and he specializes in custom spring design, including how to optimize for performance and scale. John Kahn is a product manager at MW Components Logansport. He has more than 20 years of experience in mechanical engineering, product development, and design. His specialties include hardware design, process engineering, tool design, and problem solving for spring design challenges. Before we begin the presentation, I'd like to let you know the structure of today's event. This webinar is expected to last around 45 minutes to an hour. First, our presenters are going to go over the presentation, and once that's complete, we'll go into a question and answer session where we can discuss any questions that you have about specific applications, tolerances, or other topics of your choosing. We do encourage your participation and look forward to addressing your questions during that session. Once we've completed our Q&A, we'll go into wrap up and closing. However, as you think of questions during the presentation, feel free to submit them in the Q&A section at any time. You can access this by clicking on the Q&A icon at the bottom of your screen and typing your question into that box provided. Depending on the nature of your question, we will either respond immediately or questions will be addressed at the end of the call during our designated Q&A session. I will now let our presenters begin.
Thank you, Lacey. Hello. My name is Chris Koska. I'm the plant manager / engineering manager of our Schiller Park location, formerly Mohawk Spring. And today we'll be reviewing tips for designing custom coiled springs to achieve a desired performance and specific tolerances. The topics we're going to be covering are going to be spring design process. We're going to discuss various spring types and end configurations. We're going to discuss various material types. We're going to discuss how we calculate spring rates for various types of springs. We're going to discuss the spring index. We're also going to discuss load force versus torque and discuss custom spring tolerances. So first, we'll start with the spring design process. Spring design process is the basic process of how do you come up with the spring you need? What are the basic requirements to decide if you're going to use a compression spring, a torsion spring, or an extension spring? So first we have to identify the function of the spring. So what kind of force is the spring going to apply? Is the spring going to compress? Is it going to twist? Is it going to stretch? We want to understand the position of the spring in the application. What type of spring is it going to be? A static application, dynamic application? What kind of space it occupies? But the most critical functions that we really need to know is definitely load and rate of the spring and the envelope it's being worked in. Having that basic information will help guide to what type of spring you need. We're going to talk about three different types of springs. First one is a compression spring, which could have constant or variable spring rates, various types of ends, open, closed, square ground. We're going to talk about extension springs, a little bit about how to get their rates, what type of end configurations. We're also going to touch up on torsion springs, understand what a torque is versus a force, open and closed wound torsion springs, the differences, and the various different leg configurations. So when we talk about a compression spring, there are many different types of compression springs. But the ones that come up a lot, or the ones that we see the most, are your constant pitch. your constant pitch is basically the spacing between the coils are the same. And typically that type of spring is going to give you a linear rate. You have variable pitch springs. A variable pitch spring is a spring that has two different types of gaps or spaces in the coils, and will help achieve if you're looking to change the rate curve of a spring at a certain position. We have hourglass springs that are used for confined spaces. You could design an hourglass spring to basically compress down to almost one single wire diameter. There's barrel springs, which again help you achieve variable rates, and a conical spring, which is also a very common design spring, which the advantages are you could design the same spring dimensions and get a higher rate in a smaller space. When we talk about end configurations, the most common ones we see are open, not ground, open ground, closed ground, and closed, not ground. When trying to configure extension springs, you'll see on the right there are many different types of hooks we could put on a extension spring. And typically the most common ones that you'll see is a single full loop or a machine loop. There are machines that are designed to manufacture those types of ends right off a machine, and each one offers an advantage and a disadvantage. So your single full loop or like a crossover loop has a much larger radius on it, which will allow you to achieve a longer life in the spring, but you're limited to the free length of the spring. Unlike like a machine hook, you could make the hooks much smaller, you can make the radii much smaller, so you can make a shorter spring, but the disadvantage is you'll have higher stresses at those radii points. For a torsion spring, there are basically two combinations. There's the single torsion spring and a double torsion spring. And the big differences between them is a double torsion spring, you're basically able to spread out the torque of that spring through a longer linear distance. So if you have a single spring and say you wanted it to be, over like a 5-inch length, you would, instead of making a spring, say, with a much smaller wire diameter to achieve that, you could just use the same wire diameter number of coils and just make a double torsion type configuration. The configuration of the position of the legs could be at any orientation. You can have it at 0 degrees up to 360 degrees. The radii, basically, we'd like to see at least a minimum of a wire diameter when we put a bend in a part on a torsion spring. Anything smaller than that can be done, but requires some customized tooling. Here we're going to discuss some different various materials. The most common we'll start with is your carbon steels. They offer a high tensile strength. They're very low in corrosion resistance, low in the operating temperature. Their average conductivity and the cost is average. Alloy steel, which is also similar to carbon steels, but they offer a better advantage when it comes to the operating temperatures. So they're high in tensile, low in corrosion, but we're able to use them at much higher temperatures than your general carbon steels. And the cost is relatively higher than your carbon steels. Your stainless steels, they have an average tensile strength, but the advantage to a carbon steel is very corrosion resistance. They're much better when it comes to temperatures, higher temperatures. They're not very conductive, average conductivity, and the cost is high. Then we have your non-ferrous alloy category, which is low on the tensile range, much lower than your carbon steels, but they're very high in corrosion resistance due to their high copper content. Operating temperatures, they are medium. You can't really use them in very high temperatures, but they have a big advantage on conductivity. We see some of these springs used on circuit boards and various applications where you want to have you want to transfer some electricity between one system and another. Cost is very high due to the copper. And then the last category is your high temperature alloys, which are average in tensile strength, but very high in corrosion resistance due to really high nickel in them. And of course, the operating temperatures are really, really high as well. Some of these alloys can be used as high as 900 degrees Fahrenheit. They're not as conductive as your non-ferrous alloys, and they are high in cost. So from that chart here, we'll just kind of name a couple of different types of materials in those categories. So your high carbon spring wire, the most common material would be your music wire, your hard drawn, and your oil tempered. That would fall in that category. Your springs, stainless steel wire, your most common one is your 302, your 316, and 17.7. Your 17.7 would be the higher of the tensile and lower in the corrosion. Your 316 would be basically your lower in tensile but higher in corrosion resistance. And your 302 is kind of in the middle. When the non-ferrous alloys, the most popular ones are phos bronze and beryllium copper. Both of them have very high conductivity and good corrosion resistance. When it comes to tensile, your beryllium coppers are typically higher than your phos bronze. When we get into your alloy wires, you have your chrome silicons and your chrome vanadiums. And the main difference between the chrome vanadiums and the chrome silicons is just the tensile strength. The chrome vanadiums have a much higher tensile than your chrome silicons. And for the high temperature alloys, the most common ones are your X750s. We see a lot being made from spring wire. Those just, again, our advantages is they are high in tensile. They definitely offer great corrosion resistance, and they definitely have the use in higher temperature. So now I'm going to turn it over to John.
Thank you, Chris. Starting with a basic calculation and one of the most important factors in designing a custom spring, the spring rate, what we're all after and how the spring functions, how it carries load. The spring rate is just simply defined as a load over a deflection. Basically, you're taking a load that you desire or need from this product, from this spring, over a specified distance, specified range. That is it in its simplest form. You can see here the formula from which that is derived using the modulus elasticity of the material. Again, the wire size that you pick for your design, then divided by the mean diameter from your calculations and the active material. And that is just the bare necessities of figuring rate. But when you decide on a rate, the load and the deflection play a most vital role in this. We'd like to try, in all efforts, you'd like to try to keep that rate linear or a straight line through your design, through the design of the spring itself. Keeping in mind that there are certain areas in that spring design that you need to be aware of, such as the deflection itself. You'd like to keep your first load or an assembled load somewhere out of that first 20% of the total deflection. And then on the back side of that design, you'd also like to stay away from coil bind or solid height. So you need to stay away from or have your second load, if desired, before that that occurs, before that occurs in the design of the spring, basically right around 80% of the total deflection. This will potentially give you that linear curve that you're looking for. Calculating spring rate, there are two types of spring rate. On the left here, you see a linear curve, a nice, very nice, consistent from once you start to deflect until the very end, until you get to, let's say, your secondary load or even a third load, right before solid. So you've got a nice, smooth curve. Now on the right side, looking at a variable spring rate design, it's almost like packaging two different types of springs into one design. You can utilize the pitch profile of the spring itself in order to pick up your first rate, and then as that eventually closes out your active material, your coil count, you can then choose to give that a variable pitch, if you will, a different style of pitch, space between coils, and that in turn will either basically kick your rate up beyond that linear and give you a dual rate. It just helps if you've got an area or something in your assembly that requires that additional rate, that additional load that you need to pick up prior to the coil binder solid. It's just another way of designing almost two springs into one, so to speak. One of the critical things that come into play during the design of the spring, and it also plays a specific role in how to manufacture the spring as well. The spring index is simply defined as a ratio, and we use this ratio in manufacturing to determine where it's going to be built. Basically, the spring index is just the mean diameter of the spring itself divided by the wire size. Typically, the range that you'd like to see in this ratio is anywhere between 4 and 12. Anything below a 4, you're risking tool breakage. You're risking also breaking the wire as it's being formed. It's just hard and difficult to form something around itself, if you can imagine that, wrapping the wire around itself. It's just very, very tough on the equipment and in the wire and the spring design itself. So in designing something and you're left with a minimum space, try to remember that the index does play a key role in determining how it's going to be built. On the flip side of that, moving away from a ratio of 4 on up to 12 starts to resemble more of a slinky, if you will. It gets a little bit unstable. It can be made, but again, anything on upwards of around 10 to 12, you start to get into whether or not it can be manufactured from the standpoint of clearance issues with maybe a pitch tool versus a cutoff. It's potentially going to have some issues with interference as well. But then also that your tolerance level as well. It's hard to hold something that's enlarged so much that it's unstable even in the free state. So typically what happens in a case where the index is that large, you need to either cradle the spring as it's being made or have some type of support there so that the spring as it's being formed stays away from any potential movement or of that nature. But it can be made. It's just one thing you need to consider in the design of a spring itself. Load force versus torque. The main difference between a force and a torque, not only the units, typically metric, you're dealing with newtons, and then a torque value is Newton per meter, or loads in English, pounds and pound inch. So it's just a matter of the difference in the spring design itself. Typically, you see force from a compression spring or even an extension spring where you are actually deflecting as in a regular standard compression spring or barrel shape or conical. You're deflecting to a specified height and you're picking up load. In an extension, you're actually extending or pulling to receive or get that load out of that spring. Whereas with a torque, basically centered around a torsion spring where you are bending, creating a moment about a specific axis and picking up an angular deflection. You're still deflecting, but you're not moving in a vertical or a horizontal. You're deflecting your angular deflection, picking up that moment or that torque. One of the most, besides the index, one of the most critical things that come into play, typically some of the things that we experience, and I'm sure Chris as well, when it comes down to a spring design, a lot of times that's the last critical item that's thought of. So you're left with a space, something that you have to have a spring assembled into, and you're running tight on your own tolerances, and stack ups are creating less and less room. But keep in mind that as you design this spring, there are specific manufacturing tolerances that need to play a role in how you design it. And they vary for different types of springs. But the biggest thing that you need to focus on is the body diameter and the freedom. They typically are dependent on the wire size that you choose and the index. Load tolerances, more or less a component of the rate and the free length. And they can be held anywhere between 3 and 8%, sometimes a little bit tighter depending on the nature of the spring and how the parts are gauged and actually built coming off the equipment themselves. Block tolerances do not apply. The standard block tolerances, they do not apply to the manufacturing of a spring. But over tolerancing, again, that is something that can happen. Tolerances that interfere with each other, or they tend to overcompensate for trying to maintain distinct characteristics, such as a free length tied to a load. There could be some situations where you could have one tighter than the other that would create additional output or additional operations to maintain that, not only that free length, but that specified load. So they play hand in hand with each other. So it just tend to be aware of what you need or what you desire in that assembly or in your spring design. To keep in mind those different things that can affect one or the other. A little bit more about over tolerancing. The rate is supposed to be, you'd like it always to be, linear between 20 and 80% of the deflection. That's standard. Why 20 and 80%? You typically see or have a difficult time in maintaining or holding a load within that first 20%. Just because you're just starting to get into the active material of the design. Anything beyond 80% of the total deflection, you're risking running into a solid height issue or even a coil bind. It's where you actually move away from a linear curve into more of a exponential curve where the load tends to increase rapidly on you as you decrease the amount of active material. But to meet precision spring industry load tolerances, you should always try to specify that rate in between that 20 and 80%, in even your load situation as well. And if 2 loads are specified, you shouldn't shouldn't it shouldn't provide a free length tolerance. If you'd like to keep your load within 3 to 8% of tolerance, that should be more than enough to keep free length where you need it to be. Basically, your free length figures or helps to determine where your first load or how you're going to control your first load. That second load, if desired, which typically we do see a couple loads specified on most designs. That second load is based on your rate and active material. So by the time you get most material and your spring built, the free length doesn't play tolerance or doesn't play into figuring that second. It's only that first load that free length is critical. But as far as the rate tolerance, consider your coil count should be a reference dimension. And again, only one load or three heights can have a tolerance. We don't want both. In the rate calculation, both the forwards is simply load over deflection. Compression spring tolerances, moving from the top left there. Typical coil diameter tolerances. And this is your diameter, could be an ID or an OD. Just simply looking at wire diameter compared to your spring index. Moving over in just a nice, very nice table format and figuring your overall tolerance. Moving to the other right side of the page, we have a rate tolerance specified in percent, plus or minus percent, compared to your wire diameter and active material that's already calculated in your design. We also have, depending on the application and also as far as solid height, you tend, not always, but you tend to want to have a tolerance on your number of coils, because it can vary. But we don't typically see a coil amount or total coil tolerance on any of the points that we normally keep. Normally it's a reference dimension at that point, because the active and the total coil do play a role in figuring it. Continuing with spring tolerances, your free length tolerance, very simply stated, you have specified length you're looking at, or you determined that I would like to have this length compared to your ratio of index ratio. It gives you just a nice, simple manufacturing tolerance. And it's pretty well standard throughout the industry as well. Extension springs, a little bit different, but still follow some of the same rules for compression springs as far as the free length tolerance and body diameter tolerance. Get a little bit different because of the end condition situation. On the bottom left there, gives you the total number of coils and the angle between your formed ends, whether it be a loop or a hook. Just some of the different things seen in the manufacturing world of trying to maintain an extension spring. And that's a different animal. They do have, not shown here, but you do have initial tension. The amount of force used to keep the coils closed together. That does play a role in not only your rate, but your load condition as well on the extension spring. Torsion spring, again, very different animal, and just simple coil diameter tolerances compared to your index. And again, bottom right, free angle tolerance, just because of the way the ends are conditioned on a torsion. You either have a straight leg, or you would sometimes tend to have an angle or a dual angle, so to speak, on the ends. But in any condition, they're going to have from one end to the other, it's going to be an angular relationship. And this is where I'd like to hand it off to Lacey.
Okay, perfect. Thank you, Chris and John. John, if you want to go to that next slide, we're now going to start our Q&A. As a reminder, if you have questions, please enter those in the Q&A section now at the bottom of your screen, and I'll read them aloud for everyone to learn from our presenters' responses. If you do have questions of a proprietary nature, you can send an email to either one of our presenters and they'll be happy to answer your question privately. Their contact information is shown on the slide on your screen now. Okay, so we're going to go ahead and get started. We did have some questions that were submitted in chat earlier on, so we're going to start going through those now. Question number one, what are the different grades of tolerances for springs?
So there are typically two different grades, the commercial grade and the precision grade. And the main differences are where on one of the slides you saw those charts. So when you follow the precision grade chart, you will see a different set of tolerances, typically a little bit tighter than the commercial grade. So a lot in the spring industry, over time, the tolerances that were developed were actually classified into two grades versus just having one that you probably would have seen many, many years ago.
What are the typical load and rate tolerances for compression springs?
That's a good question. So typically load and rate, we'd like to see 10% for the load and 10% for the rate. But if you look at some of the charts in the slides, actually as the spring index gets larger and your free length gets longer, the 10% really don't apply. You'll be using that chart to define it, but rule of thumb that we use is 10% is a good start to use for both load or rate.
Okay. Can you make an extension spring with zero initial tension?
Yes and no. If you make it with a zero initial tension, then it really isn't an extension spring, because then the coils are open and it behaves more like a compression spring. But there are some extreme applications where we were able to work with a customer design to make that spring behave both as an extension and a compression. So to answer the question, yes, you can in some very certain circumstances.
Okay. If I want a less expensive spring, what material or materials should I choose?
Yes. Looking at the design itself and determining how you come about what factors are used. Now we're coming up with a design, but what material should I be starting off with? As Chris first spoke about the materials in the section earlier, I'd like to start off with our basic carbon steel, the TMB, your music. And we typically follow a TMB. That's one of the cheapest and most readily available wire form, if you will. And then quickly followed by music wire, and then moving on up into the carbon alloy, jump up into the chrome silicon, or even a chrome silicon valve, or vanadium. But those are dependent upon, you have to keep in mind the stress level. What are you actually after? The cheaper material, they only have a specific temporal range. So you don't want to create the bias plane that's made out of PNB with a stress range clear up into the 80% range beyond the actual moment or actual elasticity of material. You won't be able to have this spring work at the same time. So a lot of it is dependent on how the spring functions design itself. Cost sometimes can be a factor, but if you'd like the spring to continue to work and function as it is, you got to keep in mind the simple strength of the material.
John, your audio is a little bit garbled, but I think John's point was basically it depends on the stress level and spring design as well. Those are going to be affected by the material that you choose. And we're happy to work with you guys to figure out the right material for your application. So we'll move on to the next question now, which was about 3D printing. This individual wanted to know if we can 3D print a compression spring, would that function for their application? And if they were to send us specs, could we print them a sample in this way?
So I read a lot of articles in my career, and I believe I've not heard of a spring being 3D printed yet. So springs are cold formed, majority of them. So you're taking material in a very hard condition and forming it using feed rolls, and you're pushing that material through, and it's already in a very hardened state for it to function. 3D printing, I believe you're dealing with materials that are not in a hardened state and melting them and trying to create a shape, which would be difficult to get a shape to be, round and wider. I know there are, if you visit our website, we could provide you more information. There are other things we do called machine springs, which may fit your application. It's not a printed spring, but it's a spring that actually gets machined out that has some unique applications. And I think if you visit our website, you can find more literature on that.
And we do, just to clarify Chris's point there, we do offer prototyping as well. So if you're looking for a prototype, we can create that. We just wouldn't use 3D printing for that process because you wouldn't want that type of spring for your application. You're going to want something that has greater durability. So feel free to reach out to us for prototyping needs. We did have a question about induction hardening. So if one of you gentlemen wants to cover if we offer that, and then, yeah, I'll just let you cover that first.
Yeah, the induction hardening, we do have, in Logansport, we do have a process where we do actually use electricity or induction heat treating. It's not the typical manufacturing standard that follows the induction heating. It's more or less a custom design for a specific type of spring. But again, if that is desired, it would just be a matter of looking at the design to see if it's compatible with the equipment that we have. Now, there are some spring manufacturers out there that do specific induction heating, and as far as I know, it's very successful. It mainly is used to stress relieve the part. We use it here to actually harden, heat treat the part, and then we quench and follow through with a draw type furnace. So actually we're starting off with annealed material and then follow through with that induction heating into a quench and then harden. So it's just dependent on what type of design or what type of application you're looking at, whether it's just made from standard tempered material and the induction process is then used to stress relieve the part rather than a standard belt run furnace, which is a lot of times faster and quicker. But we do not have that type of application in-house at the moment. We just have mainly a specific customized style that we follow for a specific design.
Okay, perfect. Thank you, John. This question is about the tolerance charts that we had earlier in the presentation. And so somebody wanted to know if those are available as a PDF document, if those could be emailed or sent out or downloaded in some way.
Absolutely.
Yeah, definitely, absolutely.
Perfect. So we can also follow up to individuals who ask questions after the call. So I'll take note of that one and we can follow up to get further information about what you might need and give instruction there. Next question. Would a spring that goes through a 450 degrees Celsius temperature lose its spring if it goes back down to 125 degrees Celsius?
The answer to
Yes.
that, go ahead, Chris.
Sorry, John, go ahead. No, go ahead, John. I'll let you have it. You can have this one.
In order, if you heat the spring up, if I'm understanding the question correctly, just to re-verify, heating a spring up to 425 degrees Fahrenheit and then lowering it down to 125 degrees, it depends what type of material you're using. Anything from a carbon on up to a carbon alloy, you're not even coming close to the stress relief temperature. Basically, that temperature of 425. The only thing that you might do to the spring, and it depends again, stress-wise, what kind of stress level you have on the spring. The higher the stress, the more chance it will take a sag or a loss in load, just dependent upon that level of stress. But typically, that difference or that drop in temperature shouldn't have, in some of the designs I've worked with, and Chris might have a few ideas on this, but typically it doesn't affect the spring that much. Now, from a standpoint of post-processing the spring, we utilize a temperature setting right around that 425 degrees Fahrenheit in order to capitalize on what shock peening does to the spring, in addition giving it an additional fatigue life value, helping with the level of stress there and adding good stress to the spring itself. But typically that temperature drop or range will not affect a spring that much, depending again on the level of stress involved in the spring or with the spring material.
Okay, for our next question, it says for variable spring rates, the example given shows spring rate increasing with increasing deflection. Is there a way to design a spring with decreasing spring rate as deflection increases?
John, I'll take a stab at this one. Not that I know of. Spring, as you can see on the charts and the graphs, springs are made to a height in a static condition, and as you press them down, that material, the coils are touching one and the other, so you're getting less active material. So with that less active material, that force just naturally wants to go up. I don't know of a spring that we can do the reverse with. That's not to say that the future won't hold some new ideas on that. But John, I don't know if you've heard of anything.
Yeah, I'm just trying to envision that, because typically in the work I've done with variable rate has only been compression spring or even a barrel shave. So you're utilizing the pitch, the distance between coils, in order to close one out and let the other one carry the load. And your weaker rate is typically in the small pitch, the small opening. And as those openings close, based on your deflection, you're left with a much wider opening or a much wider pitch between coil, which leads to your secondary rate or your higher rate. But it's just the opposite of that I have not seen that in the designs that I've run across or even quoted.
Okay. And then we had a question about spring production. Do springs typically require heat treating during production?
That's
Okay.
go ahead, Chris.
No, you had that one, John.
Heat treating, especially in metal forming, it can be taken two ways. Heat treating, utilizing from a material starting point of using annealed material. You're starting with a very soft or pliable metal, and you want to heat treat it to a more usable, a tangible form to get it into a tempered form, basically, to where the hardness is going to give you some elasticity. But in general, we like to refer to it as a stress relief. You are throwing heat at the spring or the product, but you're not at the heat treat temperature level. Typically, heat treat temperature levels are range anywhere between depending on material again, range anywhere between 1200 and 2000 degrees. Whereas a stress relief is anywhere from 400 on it to 850 degrees Fahrenheit. So with a stress relief, you're just basically giving that spring, once formed in the tempered material state, you're just relaxing those forming stresses you put on it to pull it from a bundle of wire into a nicely coiled spring, whether it be a torsion, extension, or compression. You're just relieving those stresses that you put on it in cold form. You're not really changing the material content or adjusting cell structure or going from a austenite to a martensite. No, it's just, that's what it is, relaxing. So it's really not a heat treat. But on the other hand, when you're dealing with a much larger spring, anything from a 1/2 inch diameter on it to 2-inch bar size, there you're dealing with a heat treat condition to where you have to actually heat the bar up before forming and then quenching and running through a draw furnace. And you're actually performing a heat treating process at that point. So it's just dependent on the material and what you're looking at as far as the design itself.
Okay, next question. Does a spring with a variable pitch does the spring with a variable pitch have different rate tolerances and or total spring life cycle?
Yes, it would have a different rate tolerance, and it could have a different spring life cycle. We would have to run, if we had the information of the exact OD, free length, number of coils, what that rate target is, we can definitely provide you with that information, but that is not something that you could probably find off of a chart that's available. We have to actually put that through some design software to calculate that for you, but it would have different tolerances.
And then we had a couple related questions. The next one was, what sort of order quantities are needed for custom variable rate springs?
As I know, speaking for a Schiller Park site, we can do one spring, to 5-10 springs. Coiling a variable pitch spring is not too difficult, so it doesn't require any, additional tooling or anything like that. So, we can, do as little as one spring if required.
Okay, and then to your software comment, someone did ask if we use advanced spring design software.
Yes, the Schiller Park site does. Some of the other sites may be using something different.
Absolutely. We utilize that design, that software on a daily basis. We also have specialty software that will capitalize on variable rate spring design, along with variable bar as well.
Do we offer small leaf springs?
We did at one time. That was a kind of a niche for our hot forming. But at this time, that equipment has been moved elsewhere, and the business decision a long time ago was to get out of the leaf spring.
Okay, thank you. We do, to everyone's knowledge, we do offer leaf springs, not the smaller styles, but we do have some leaf springs available through Hyper Coils, which is one of our in-house brands, but not the smaller versions. Let's see, what is the typical time it would take to receive a prototype torsion spring, particularly with a wire diameter of around 0.3? Chris, I know your site does prototyping. What's the typical turnaround time for something of that nature?
So I can't speak to the 0.3 because that's a really large wire diameter. It's kind of over our site's capability. But a typical prototype, if it's a material that's in stock, should be willing to ship out. If it's nothing that requires any type of end condition, some kind of bends at the ends, but if it's just a simple straight leg torsion spring, if the material's in stock, it should be within a couple weeks. You should be able to get prototypes. But again, it really comes down to the material and any kind of end finishing that's going to be done on it. That could definitely change that lead time.
And we do offer prototyping at other sites as well. So outside of the capabilities that Chris had mentioned. So I would recommend just reaching out for a custom quote, and we could pair you with the site that would be able to produce it. And obviously lead times are going to depend on that specific site, but to Chris's point, usually within a few weeks. Next question is, what design considerations go into torsion springs to prevent binding and to allow the spring to only experience rotational movement?
I really kind of don't understand the question. So to prevent binding, I'm thinking it's the binding that occurs when the coils are touching themselves. I'm making that assumption, but I could be wrong. But I think that the easiest method is to you could put a space in between the coils, so you could design a torsion spring with space in between, where as it's deflecting or doing its rotation, those coils don't touch, they don't bind or create friction. That's what I'm assuming it is, but if definitely you could reach out to me with, maybe I could talk it over the phone with them when I get a little more detail, but based on that question, it's the only thing I could think of.
Yeah, it could be a case of where the torsion spring itself has gone beyond what it was designed for in trying to pick up more load. Just a simple maybe body diameter or even a wire diameter change that would allow it to flex more without binding up.
Okay, the next question is there any design information that could be provided to me regarding flat bar torsion springs?
That would be, I believe, just a simple beam calculation. And yes, that information is available from the books that we've got. We typically haven't built that type of torsion bar, or we don't have the capability here. But again, it's just a matter of finding the right formulas, and those are available in most spring design books.
Okay, and then we had one more question about a specific application, and I hope I'm understanding this correctly. So let me read that and see if we can get an answer from you guys on it. I put some new springs on my car a few years ago that had dead coils, I believe there were variable springs. They bottom out under the load of the car. What exactly was the point of those springs? Is it to add overall length?
Are these, and I suppose the question didn't specify that we're assuming they're suspension springs.
It sounds like suspension coils, yes.
Yeah, and I would guess that those dampener, that's exactly what they are, dampener coils, in order to control maybe not variable pitch, but they might be there for just a kick from one rate to another, not giving you so much of a drastic change, but more or less trying to control when you are on a cobblestone street compared to a nice flat blacktop, give you a little bit better ride. And those dampener coils there, or those closed coils, are there to handle that, or to give you a little bit more ride control, a little bit more better feel in the conditioning of whatever you're driving on.
Perfect. And that individual did follow up. It looks like that question was answered. So thank you for that, John. We appreciate it. One last question that we have in the queue. Do you make wrap springs with super tight tolerances to act as a clutch wrapped around a solid shaft?
I am not familiar with that design, but I'd be willing to take a look at it and just to see if that's something that is one of our things that we can make here. Not familiar with that design.
Okay, great. And just a reminder, we do have over 20 different sites, many of which do springs. We have 2 of our representatives here today from individual sites, but even if our gentlemen here today do not have the capability within their facility to make certain styles, we do have that capability most likely within another facility. So I would generally recommend just reaching out for a custom quote, and we'll be happy to partner you with the best facility to make that spring, custom or otherwise. Okay, so this does now conclude our Q&A. If you do think of additional questions, feel free to reach out to our presenters at their respective email addresses, and they'll be happy to assist further. I would like to thank our presenters and all of you for joining us. We will be following up through email with a link to the recording so that you can share it with your peers or use that for reference later. As a reminder, MW Components manufactures stock and custom parts, including springs, fasteners, bellows, couplings, and other precision metal and plastic components. We accelerate the entire process of delivering stock and custom parts to almost any volume or tolerance and against demanding deadlines. With MW Components, you can be sure you'll get the right part to the right specifications each and every time. For more information on MW Components products, services, and available resources, including white papers, case studies, and webinars, visit mwcomponents.com/resources. This now concludes our webinar. Thank you all for listening and have a great day.